Why can a machine learning system make unfair decisions even when it appears objective? This happens when bias in data, design, or decision processes leads to harmful outcomes for some groups. You are about to trace what algorithmic bias is, how to detect it, how to measure it, and how to reduce it. Algorithmic bias refers to systematic errors in machine learning models that create unfair or discriminatory outcomes for certain groups. Detecting and addressing this bias matters for fairness, equity, and trust. In practice, bias appears when predictions disproportionately favor or harm particular groups. Bias in artificial intelligence often begins in three places. It can come from data bias, algorithmic bias, or societal bias reflected in outcomes. Understanding these sources is important because unfair and inaccurate results rarely come from one issue alone. Data bias originates from the data used to train machine learning models. It can come from underrepresentation, when some groups appear too rarely, historical bias, when past inequalities are built into the data, and sampling bias, when data collection favors some groups or excludes others. Algorithmic bias can also be introduced during model training or decision-making. Causes include model assumptions that miss complex patterns, feature selection that uses proxy variables for sensitive attributes, and optimization goals that prioritize accuracy over fairness or equity. The result can be unfair treatment and discrimination. Some bias mirrors existing social inequalities. Historical patterns can be reproduced by artificial intelligence systems and then amplified through automated decisions. This means a model may not just repeat unfairness, but help spread it into areas such as hiring, policing, lending, and education. 0, 2, 0, 3, 0, 4, 0, 5. The material gives several clear examples. Facial recognition systems can show higher error rates for minority ethnic groups because training data underrepresents them. Hiring algorithms can discriminate against women when historical data favors men. Credit scoring models can assign lower scores to minority groups when socioeconomic disparities are reflected in the data. Specific cases show how this plays out. Amazon's artificial intelligence hiring tool discriminated against female candidates because of historically male-dominated hiring patterns. The Compass recidivism algorithm showed higher false positive rates for African American defendants. Google Photos misclassified people of certain racial backgrounds because the training dataset lacked sufficient diversity. Bias detection begins by looking closely at data and model behavior. You analyze representation in the dataset, evaluate performance across demographic groups, visualize disparities, and monitor feature importance. Together, these steps help reveal where unfair predictions are coming from. The first step is to analyze data representation. You check for underrepresented or overrepresented groups and make sure the dataset has diversity and balance. Exploratory data analysis supports this by examining distributions and revealing imbalances before model outcomes are accepted as fair. Study distributions early. Review group diversity. The next step is to compare model performance across groups. The material points to measures such as true positive rate, false positive rate, and precision for different demographic groups. Differences in these results can indicate that one group is being treated less accurately or less fairly than another. Disparities become easier to spot when you visualize them. Confusion matrices and fairness dashboards can highlight performance gaps between groups. Feature importance analysis then helps identify which features contribute disproportionately to bias predictions, including proxy variables that may indirectly encode sensitive attributes. Another detection technique is simulation testing. This means simulating outcomes for different groups to identify disparities in how the system behaves. Used alongside fairness metrics and exploratory analysis, Simulation testing adds another way to check whether a model treats groups consistently. Bias metrics are essential tools for judging whether machine learning systems treat demographic groups fairly. They help identify disparities in outcomes and support alignment with ethical standards. The material highlights several common metrics, each focusing on a different aspect of fairness. Statistical parity difference measures the difference in positive outcome rates between groups. Its purpose is to identify disparities in overall outcomes. One example is a hiring model that favors men over women for job offers, showing that the distribution of positive outcomes is uneven. Equalized odds requires equal true positive and false positive rates across groups. It is used to evaluate fairness in predictive accuracy. The example given is a loan approval model with higher false positive rates for minorities, which signals unequal error patterns in the predictions, 0, 4, 0, 5. Predictive parity means equal precision across groups, so prediction reliability stays consistent. The example is a credit scoring model that predicts defaults more accurately for one group than another. Demographic parity means equal proportions of positive outcomes across groups, such as a college admission system favoring applicants from a specific region. Fairness through unawareness removes sensitive attributes from the model, which can simplify fairness analysis by removing explicit bias. The example is a recruitment model that ignores gender as an input feature. The material also applies metrics such as disparate impact ratio and equal opportunity difference in hiring, loan approval, and admission systems. Several tools support fairness evaluation. Artificial Intelligence Fairness 360 from IBM is an open-source toolkit for identifying and mitigating bias in datasets and models. FairLearn from Microsoft helps assess and improve model fairness. And the What If tool from Google supports visualization and analysis of predictions for fairness evaluation. Bias in artificial intelligence decision-making can lead to discriminatory outcomes, ethical violations, and loss of trust. The consequences extend beyond technical performance because decisions affect access to jobs, loans, education, and public services. This is why bias is both a technical problem and an ethical concern. Biased systems can violate anti-discrimination laws, damage public trust, and expose organizations to fines or sanctions. They can also deepen social and economic disparities for marginalized groups and cause reputational damage or emotional distress. The examples include hiring systems favoring male candidates and facial recognition errors affecting minorities and women. A bias mitigation strategy starts by identifying where and why bias exists. You conduct exploratory data analysis, evaluate performance across groups with fairness metrics, and identify features or proxies behind biased predictions. Then you choose pre-processing, in-processing, or post-processing methods that match the problem. Pre-processing changes data before training, such as rebalancing datasets or removing sensitive attributes. In-processing adds fairness constraints during training, including regularization terms or fair adversarial learning. Post-processing adjusts predictions after training, such as calibrating probabilities or changing thresholds to equalize outcomes. The material recommends data diversity, continuous monitoring, stakeholder involvement, and transparency. Case studies show these ideas in practice, including loan approval, fraud detection, healthcare, job recommendation, and customer support systems. Reported outcomes include improved equity, more balanced performance, and better representation without significant loss of accuracy in one loan approval example. Unfair machine learning decisions can be traced to biased data, model design, and wider social patterns. You have seen how to detect bias, measure it with common fairness metrics, understand its consequences, and respond with structured mitigation strategies. fairer artificial intelligence depends on careful analysis, appropriate tools, and continuous monitoring.